everyone. Sorry for the 1 hour delay we had for lunch. So we will now begin our next session of the undergraduate symposium. The talk will be, everyone will give a talk of 12 minutes. A 10-minute warning will be given. So let's begin by Junik Sengupta from BKC College.
Well, so it's indeed a pleasure to stand in this platform and be able to deliver some words with everyone. Now, due to the shortage of time, I might not be able to cover the entire part of the talk, but by the end of it, I can assure that you will get some knowledge about whether we should hunt for any other home or we should not. So let's just begin with. Now, the very basic journey starts with here, with our home. Now, just like this hall is made up of different bricks, pillars, chairs, and everything else, our home is also built up of very fundamental things that defines whether it's a home or not. That is water, sunlight, natural sources of energy, minerals, and everything else, which is most importantly the atmosphere. So the very basic point by which we define a planet which is habitable for living or not is these conditions of a proper amount of sunlight, water, energy, and etc. Now, we were happy inside our place, so why should we search for an alternative? Well, one fundamental reason to search for an alternative is that the natural disasters that might just cause a destruction in a very few seconds. Well, I'm not talking of COVID or anything else, but I'm talking of tsunamis, meteors, and anything else like that. By using electricity and burning cigarettes, we are actually losing a lot of these fossil fuels. We are burning them. And another possible need for to search for another habitable planet might be whether life form does exist or not. Unfortunately, I think my animations are not working in this slide, but in my one, I've created some sort of animations which might make them a little bit more interesting, probably. So the very basic reason, the very basic point from where it started was the Kepler Space Telescope that revealed that there are more planets. Can I just, I think some points in the slides are missing. Will it be possible if I... Oh, this is the PDF. There was a slide, PPT PowerPoint along with that. That was I told you about. Will you just change it or I'll just continue it over here?
Do you have a pen drive which has it?
Yeah. I already have it in my drive also. Yeah, obviously. Or I can just continue it here. It's no problem in that. I just send it. Yeah, so I'm really sorry for the delay. Now, what we are basically looking for is an extrasolar planet. Now, what is an extrasolar planet? Any planet which is apart from our solar system, which has these habitable conditions for life form to exist in there, could be termed as an extrasolar planet. The basic search started with the NASA Kepler telescope that predicted that there are more planets in our galaxy which are habitable for life form to exist on. Now, by measuring what we actually do is that by measuring the exoplanets, the first thing we use our telescopes to make a search for whether the planets are around our conditions to be a proper planet or it's a star or kind of that thing. By measuring the planet's mass, its atmosphere, its diameter, and everything else, we can predict that whether it is made up of gas giants or etc. And via measuring the photometric observations, we could confirm that whether the atmosphere is composed of poisonous things or whether truly life can exist in there. Now, what is the need to look up and there? So, what are the methods by which we start this journey? The very basic method is measuring the verbal velocity of the planet, or by measuring the verbal velocity of the constituent star. The starlight, which comes from that star, on the presence of the planet, it gets squeezed at certain point of time. By measuring that, we can predict that planet does exist there. The second thing that comes over, that is the major point of this talk, was the transit timing method. Now, one thing I should mention that most of the exoplanets which have been detected till date are by this transit timing method. What we do is here, the light which is coming from the star in the presence of the planet gets affected if the planet is present over there. If you can see there, that slight dip is present because the planet, while that comes in the path of the starlight, and it causes these disturbances to get detected. Now, there are other various methods by which we can detect these planets, namely the gravitational microlensing method. If you can see on the graph over there is a slight dip or a slight kind of a spike over there, which is caused due to the presence of the star due to the presence of the planet on the star's orbit, while the starlight was getting lensed by a distant galaxy or distant star. The other one, which is quite fundamental, is the direct imaging method. Now, this is very fundamental, but yet the most complex thing, because when we are observing something at that much of a distance, it is not always easier for us to have a clear image of that. So this is a short history to when it was started. The very first start begins in 1917 when some person named Van Magen identified the first polluted white dwarf kind of a thing. Later on, with the Kepler missions, it became more precise, and further with the different space telescopes was launched, like the NASA Spitzer Space Telescope, which was majorly not launched for the search of exoplanet, but some of its observations were predicted to be of this kind. So earlier, kind of 10 to 20 years back, we might have just said that there is not much of a planet which is available for habitation. But right now, we live in a universe which is full of a large number of exoplanets, which could probably be next home in a couple of days, or maybe a couple of years or a couple of decades. Now, this is a rough estimation of what are the types of these exoplanets are. I am sure quite a lot of people over here are aware of this, so I'm not getting into some.
Yeah, it will come.
Okay.
It will come.
Good. হাত লাগলে মনে হয় চেঞ্জ হচ্ছে। কিছু হচ্ছে বলে তো মনে হচ্ছে। তুমি হচ্ছে না, জানি না ভাই, আটকে গেছে, তারপরে আর কিছু হয়নি। সেখানে না পজ করছে, আমাদের সিগন্যালের কানেকশনটা কিছু সমস্যা হচ্ছে। না, আসছে না, না এখন নেই, পিছনেই দেখতে পাচ্ছি। চলছিল এতক্ষণ? হ্যাঁ, এতক্ষণ চলছিল, কিন্তু তোমার ভিডিওটা অসুবিধা হবে? আমার অসুবিধা নেই। মানে এখানে টাইম কন্টিনিউস ক্লিক করছি তো তাতে বোধ হয় কিছু সমস্যা হচ্ছে। যেটা হচ্ছে ওইটা নিয়ে চলে গেছে যেটা দিয়ে করছিলাম। এটাকে আমি ক্লিক করছিলাম বলে কোনো প্রবলেম হচ্ছে?
না
পয়েন্টারটা পয়েন্টারটা ইউজ করতে পারি, তাহলে আমার মনে হয় সুবিধা হবে।
সাপোর্ট করছিল এতক্ষণ হয়ে যায় এই ল্যাপটপে কাজ হচ্ছিল।
এই তো হ্যাঁ মনে হয় এর আগে স্যারকে এই
না
ল্যাপটপ
আপনি কি নতুন ইয়ে করলেন, এটা লাগালেন?
না 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 এটাই ছিল।
এই ছিল। এতক্ষণ এই ল্যাপটপে কাজ হচ্ছিল?
না না এটা
অন্যটাই হচ্ছিল। হ্যাঁ সাপোর্ট করছেন।
এতক্ষণ তো চলছিল,
এতক্ষণ চলছিল অন্য ল্যাপটপে,
মানে এতক্ষণ না একটু আগে
একটু আগে অব্দি এটার মধ্যে দেখছিল।
এটা এসেছিল।
হ্যাঁ
সেটাই তো জিজ্ঞাসা করলাম। তখন অনুযায়ী আলাদা হয়। আগের দিন যে এই ল্যাপটপ ইউজ করেছিলে, যেটা তুমি করছিলে সেটা তো কখন কোথায় নেবে না নেবে বলাই মুশকিল।
দেখাচ্ছে যে প্রেজেন্ট হচ্ছে, মানে ল্যাপটপে দেখাচ্ছে যে প্রেজেন্ট হচ্ছে, কিন্তু এইটা প্রেজেন্ট হচ্ছে না।
কিছু অপশনস নেই। সিগন্যাল দিচ্ছে না এখানে, খাবো দেখতে কি বলবো। হবে না নিচ্ছে না গো। দাঁড়াও আমি একটু ক্লিক করেছি তো। নেই নো সিগন্যাল।
এই উদ্দীপন দেখ না ভাই, জানি না ভাই। Someone wants to join the call. Neil Kohli, probably one of the speaker. এই আমি বসছি, তোদের শুরু হলে আমাকে বলিস। না না এখানে
ল্যাপটপে নিয়েছে এইচডিএমআই।
প্রেস্টিজ লাগছে ভাই।
ল্যাপটপে তো দেখাচ্ছে এই নিয়েছি, এই মনে হচ্ছে যে শুরু করছে। এইখানে শো করছে, দেখো তো। এই দেখো, ওয়ার ডিসপ্লে।
দেখি ঢোকো ঢোকো অপশানে ঢোকো। দাঁড়াও।
এই যে না, এটা কি নামটা দেখো, নিচে নামো, নিচে নামো। ওটা অডিও এর জন্য।
হ্যাঁ
এই যে তোমাদের এটা এখানে
এর আগে যে সার্চ করছিলেন এটা কোথায়? স্যার
ইয়েস করি, দাঁড়াও নতুন করে আনবো।
অন্য কারো ল্যাপটপ নেই?
হ্যাঁ অন্য ল্যাপটপে একবার ট্রাই করুন, বুঝলেন?
বেটার হবে।
এটা সাপোর্ট করছে না হয়তো।
কেটে না, কেটে না, কেটে না, ওটা কেটে না।
সরি সরি, আচ্ছা আচ্ছা ঠিক আছে। সাপোর্ট নেই।
একবার খুলে আরেকবার লাগিয়ে তাহলে
দেখো তো,
রিমুভ করলে একবার।
রিমুভ করেছি, তুমি এবার লাগাও দেখি। সাপোর্ট নেবে, কখন নেবে, কি হবে কি পুশ করো। নেয়নি। অন্য ল্যাপটপে তোমরা ট্রাই করো।
ল্যাপটপে দেখে আমি সামনে আছি।
আচ্ছা
অন্য ল্যাপটপে ট্রাই করো।
করতে লাগানো যেত এইরকম ভাবে লাগাবে উপরের দিকেই এটা আছে
এটা তো পাশেরটা তো
হ্যাঁ হ্যাঁ ওরকম ভাবে লাগবে একবার লিখে দিলেই হয়ে যাবে
দেখতে পারো ওটা কাজ করছে কিনা।
শো করেছে কিনা দেখো শো করবে তাহলে এখান থেকে ধরো সেটা ওটা দিতে কোন আছে কোন আছে
হচ্ছে 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 হচ্ছে
অন আছে, এটা অন আছে, এটা অন আছে। Sorry for the delay we had due to the technical issues. Now we resume the talk of Junik Sengupta from the beginning.
এটা কোন দিকে ঘোরালে হয়, এটা কোন দিকে ঘোরালে কাজ করে? ও আচ্ছা আচ্ছা বুঝলাম বুঝলাম, থ্যাংক ইউ। Okay, so if you're still interested in knowing what I'm doing, then let me bore you once again. So we'll start from where we were, the very basics of what determines a planet, the sunlight, natural ample amount of water that doesn't look like water though, minerals, energy sources, atmosphere, all these conditions once gets characterized by it's good, so we can say that it's a planet. I'll just jump onto this, that why we are trying to make a search for the exoplanets is that probably the Earth might get destroyed by some sort of natural disaster, the fossil fuels might run out of sources, or might someday we need to search for whether life exists in somewhere outside Earth. All these things tells us to do only one thing, that is to make a search for another planet which might possibly be able to host life form apart from Earth. Now, there was a famous Copernicus paradox which says that solar system is Earth is unique to the solar system, and this solar system is unique to this universe. But we successfully proved him wrong by stating that there are a large number of exoplanets been discovered till date. The methods by which we mostly do that, but the methods by which we mostly make a search for the exoplanets, the very first one of them is the Wobble method. All of these, the first three methods that I'm going to tell about, these are indirect method. The Wobble method basically tells us that whenever there is a planet which is orbiting a star, the light from the star gets squeezed up a little bit due to the presence of the planet. By measuring that, we can kindly predict that a planet might be possibly exist there. The other one, which is another indirect method, the one which we will mostly highlight in our talk while making a search for the exomoons, is the transit timing method. Now, what the transit timing method is that due to the presence of the star, due to the presence of the planet, which sometimes comes in front of the star, the light which we get from the star gets ampered for a small amount of time. By measuring that tampering amount on a periodic note, we can predict that there is a structure which is present apart from the star over there. There's another method which is most popularly used, which we call the microlensing method. Now look, if you just notice over there, there's a slight spike on that graph, which spike was produced because the planet was present in the sun's orbit or the star's orbit, which caused a little deformation to the lensing that has been occurred over there. Now, I'm not going into details of this because the talk is not exactly about the measuring of what exoplanets are or what are the methods by which we are detecting exoplanets. So I'm just giving a rough idea of what are the ideas that we use for detection of the exoplanets. By the end of the talk, I'll give you some references where you can find detailed meaning of this, what they are. Now, the very last one of them is the direct imaging method. Now, this one is probably the best one and yet the most complex one, because to get light directly from something which is millions of light years away from us is not that easy. So mostly the searches by the direct imaging gets limited because of the distance and the time that it takes for the light. This is a short history to when it started. It early started in 1917 when some person in Van Macken did the first, predicted the first presence of the extrasolar planet by monitoring a polluted white dwarf. Later on with the Kepler search missions, where is it? I can't even see that. Oh yeah, this is the first exoplanet which was been detected, the 51 Pegasi b, which was in early 90s, which was a giant kind of a giant Earth property of a thing. With the Kepler space missions, we have figured out a large number of Kepler exoplanet searches, And there's another mission, which is the NASA Spitzer one, which is not dedicated for this search, but its results, the conclusions had given a large amount of kick to the exoplanet search. So earlier we might just think that like the early saints, the early peoples have concluded that humans live only on Earth, or the Earth is the only habitable planet. But today we can conclude that we live in a universe which is filled of exoplanets. So it's kind of, we are living in a city where a lot of room is available for people to rent or to buy. Now, these are the basic types of what exoplanets could be like. These could be the gas giants, like they could be super Earth, terrestrial ones, which we are mostly interested about. The rocky ones where water might possibly be present. There is Neptune-like, which is gaseous worlds around the size of Neptune. Now, these are the rough ways by which the ones which we have explained, and the numbers below shows how many exoplanets are, or how many planets or how many possible candidates are being found over this. You can see the major number of things was found by transit things, and the direct images has just been 2. The results was limited because, as I have mentioned, light from such a distant source is very difficult to get detected. There's another method which we call the coronagraph method, which measures basically the like the first thing that the coronagraph uses is that it diminishes the star size. For example, if this suppose if this is the orbiting star and this is the planet, the coronagraph dims down all the light that comes from the star so that we can have a clear eye on whatever the candidate which is present in its vicinity. But the method by which it is done is called a star shed. This is kind of a, I'm not sure about this thing is yet been made into practice, but whatever this thing does is that just like the James Webb telescope we have seen a couple of days before, the antennas of the James Webb telescopes opens up to protect it from the sun's radiation. This thing has those kind of shields, which is a little larger than that of the James Webb, which kind of stops the sunlight or stops the excess sunlight to come into the observation methods, and using that we can have an eye on the candidate which has been present over there. Now we come to what the talk was majorly on about, exomoons. Now, why do we need to make a search for exomoons? We were searching for planets where we can make a habitable zone. Now let us take this familiar example which is just next to our vicinity, the Jupiter. If we try to make a habitable situation at Jupiter, we can see that Jupiter's atmosphere is filled up of huge amount of toxic gases. There is excessive gravity, and the temperature is minus 280 degrees Celsius. So searching for a home in Jupiter or searching for a penthouse in Jupiter is absolutely next to impossible. On the other hand, if we try to look at Europa, which is Jupiter's moon, which is more habitable, having ice, possibly there could be liquid water, and all these things suggest that Europa, if we want to make a search for, Europa could be a better target than Jupiter to make it. Apart from that, what are the other advantages of having a moon to a planet's vicinity? The very first thing is that it maintains the wobbling of the planet, it maintains a proper climate condition, and as well as the tidal effects by maintaining the seasons. The tidal effects maintain the seasons, and there are a lot of advantages. Like you can see, the Earth's orbit is the Earth is basically the Earth is still continuing in its orbit due to the presence of a satellite system. Otherwise, it might have been long lost in space. These are some orbital structures of the different planets. If you can look at the Earth's orbit, this is not very clearly visible over here, but if you can look into internet about that, you can see the Earth's orbit is not absolutely circular, not absolutely elliptical. It is maintained in a perfect shape, and this perfect shape is being due to the presence of a secondary satellite which is in Earth's vicinity, which is the moon. Different planets other than the Earth have large number of moons like Jupiter, Saturn, and etc. etc. So if we are trying to look for a habitable zone into our solar system, the very next possible thing is to look for the moons, but not the planets. We don't want to have a home in a planet which is having a wind running at the 280 miles per hour or even more than that. Now, another obvious attempt is the theory of exomoons was first being dated in 1999, which was also been proposed by the transit timing method. These are some of the reasons why we need to make a search for the exomoons. Now, if I'm going into details, I don't think time will allow me to. How much time do I? Okay, I should just little run over there. So these are all the reasons by which we need to make a search for an exomoon. Like the very fundamental one, I'll just like to highlight. Even if we could detect an Earth-like planet in near future, the habitability will be largely governed by the presence of a moon to its vicinity. Even if we found an extrasolar planet, whether it will be habitable for, not again, please. Thank you. Even if it's habitable for life form to exist on, we need a moon, or the presence of a moon will not hamper anything, but it will make it more habitable. This is some table. You can find it on internet. You can find it on NASA Exoplanet Archive. Now, what are the possible methods for exomoon detection? The very first one is that the direct imaging method. But just like that, the direct imaging method is limited. Now, this is a short introduction to why is it limited. Suppose if we look at the Earth and the Moon's, suppose if we take the Earth and the Moon at a distance, for an example, there the angular distance between Earth and Moon is 0.5 milliarc second if we observe it from a distance of 10 parsec. Now, you know, 1 parsec is even greater than a light year. Now, the exoplanets or the exomoon candidates that we have observed till date have the angular distance between them of 25 milliarc second. So you can estimate if 5 milliarc second results for 10 parsec of length, you can estimate what distance will be 25 milliarc second will result it into. So direct observation has been limited due to this census. These are one of the two direct imaging methods which was being used, and the results was absolutely not satisfactory. Other than that, we have the radial velocity method, by which we can measure the orbital velocity of a star, of a satellite system which is orbiting the planet, which is again orbiting a star. We can also use the pulsar timing method, which is not very popular, but the first exomoon candidate was detected by the method of this. Apart from that, there are two other methods, which is again the indirect method, the one that I have also explained before, that is the gravitational microlensing. The presence of a satellite system on the vicinity causes a spike to the lensed data. And there is other one, which is the occultation method, that it is majorly like the satellite which is orbiting the planet that causes a little bit deformation to the star's light, and we can observe that to go to that. Now, the title of the talk, as explained, the transit timing variation. The majorly used and till date, the best things that we have in our hand is the transit timing.
1 minute left.
Who said? Okay, yes, thank you. So I'll just explain what the transit timing methods are. Basically, what we do here is that whenever we observe a planet which is orbiting a star, and as soon as
Complete your sentence.
Oh, yeah, okay, thank you. So whenever we have something as a planet which is orbiting a star and there is a moon to its vicinity, the amplitude by which these two systems orbit them gets changed. And this change we can monitor. Now, the very first thing, now this talk is basically a rough idea about a research work that I had done in 2020 with my team under IIA. What we did, I'll come to that. Earlier, till date, the detections was done on the basis of the transit timing methods only, which is basically a function of the satellite.
Time's up.
Time's up. I'll just end with the team slide. So we did a lot of things which even I don't understand very well what we did. And basically what we did is that we used transit duration variation thing along with the transit timing variation, which resulted in a shortlisting of a number of candidates. Where is it lost? These are the calculations that we have done. Please don't go into detail of this because I don't know what we have done. So what basically we have in our hand is that this is the amount of exomoon candidates that we have detected. Now, we have done this on the basis of the Kepler 2016 data sets. Our search is yet to be completed. These are another 53 candidates which potentially could have an exomoon, but it's not been recorded in our data. Now, these are some of the calculations. Oh, okay, just a minute. You can find all the detailed reports of our research in this website, as well as our paper was been uploaded to ResearchGate. You can just take a look at that if you want to. This is the team that we had. Other than me, everyone was working very well, fantastically. And these are some of the references. I would like to end with a quote of Rabindranath Tagore. বিপুলায় মহাবিশ্বের কতটুকুই বা জানি উনি পৃথিবী বলেছিলেন আমি জাস্ট মহাবিশ্বতে টার্ন করে দিলাম মহাবিশ্বের অনেকটাই আমাদের কাছে অজানা so there are more things that we are yet to be known. Thank you, and thank you for tolerating all these glitches.
Thank you.
Welcome.
Junita. Now, if anyone may have questions.
I have several. I will ask one. Only take
Okay, yeah, thank you. I'm sorry.
First thing is that you tell that exomoon become a potential candidate for these exoplanets.
Yes, yeah,
So, and you said the transit method is very successful in this regard.
very much.
So, when you talk of transit method, there is something we call is the limb darkening effect.
I can hear you.
So, when you talk about transit method, there is something very important. Something is very important. That's limb darkening effect. So, when you measure that, the central brightness is much. So, when you do the transit, therefore, that's reason you get a dip. So, even if that's the scenario of this effect. Why at all do you think the transit method is at all so much useful? Because in one of your slides you showed that the measured number of detection is as per, that's how you portray that the transit method is one of the best methods.
Yeah.
So why is it so as per your?
Okay, yeah. If I was able to complete this, I might have just explained your answer. The transit timing method is useful as compared to the other methods we have in mind. The transit timing method has a lot of glitches that you explained about. Even when we are using only the transit timing method, the major problem that we have is that it is a function of the distance of the planet to star system. So when we are observing another candidate, which is very small, like 5% of the planet size, it is not very useful. But when we have in hand the direct imaging method, absolutely useless, only two candidates. We have the gravitational microlensing method, not even completely detected. We have the radial time velocity, the wobbling method. Those methods have been proven to be less useful as compared to the transit method. I'm not saying transit is the best one. Transit is best, relativistic the other methods. And we have used another method of transit, the transit duration method, which has, as by working hand in hand with the PTD method, it worked a little bit.
Okay, so unique. So I have a question. The first of all is that you talked about detection of exoplanets and exomoons and all that. Nowadays in the exoplanet community, there has been a big interest in addition to like detecting them, would like to know about their atmospheres, right? Like what element. So for example, like to know about like exomoon atmospheres, for example, like cloudy model or hazy model, like this.
How do we do that?
Yeah, so how we do that? Like
Okay, so the very first thing that I am going to answer is that we haven't detected any exomoons. We have predicted their presence over there. If we can conclude that this is an exomoon, the exoplanet atmosphere is the best thing we get by spectroscopy. Even if we want to search for, even if we want to make a search for the atmosphere of the exomoons, we first need to know what are the chemical presence in its atmosphere. We need to make. I think direct imaging method will be required in that case. And as much as my point of interest, we might not be able to get a very clear idea about the exomoon's atmosphere because we are talking about candidates which is even smaller than the exoplanet size.
okay, so like I have just like you talked about something like that, like the temperature of the clouds and something like this is related to the atmosphere. One of the slides. So like
Temperature of
yeah, you mentioned in one of your slides.
oh, Jupiter's
Jupiter. How do people measure this kind of these temperatures? Like, is that due to black
If you could just email.
Can you email it? Okay. Kakinapur Precision and Precision email.
I'm not very sure about how do they do that. Probably you can just go to the Cassini and the Europe archives of NASA. There they have explained some of the methods by probably they use a spectroscopy, some sort of thing to do that.
That is not direct imaging called.
I think it might be.
Light
No,
blue,
I'm not as very good.
ডাউনলোড করে নে এসছে পিডিএফটা
থাম not us.
সরি সরি
ওপেন কোথায় হয়?
টাইম দে এইটাকে
ওই দিক দিয়ে হাত মারিস না, মরে যায় না।
উইন্ডোজ
Folder.
বন্ধ করি তাহলে না হলে প্রবলেম হবে এটাকে তো
বাইরে গিয়ে জাস্ট নর্মাল ডাউনলোড করে ওখান থেকে খুলে দেয়।
ডান
ডাউনলোড করেছি তো।
আর কন্ট্রোল এল ডাউনলোড করা আছে তো যখন তাহলে
ডাউনলোড থেকে পেয়ে যাবি প্রেজেন্টেশন অপশন।
এটা লাস্টটা না এটা
প্রেজেন্টেশন অপশন আছে না?
আরে এখন প্রেজেন্টের বলতাম আমি বলে দিই 1 মিনিট।
ঠিক আছে।
So thank you. So thank you, Junik Sengupta. Next talk will be given by Devdatta Banerjee from Indian Institute of Science, Education and Research. Please come on.
এটা অ্যাভয়েড না করে লাগবে না।
Mars, the red planet, has always been of great interest to scientists and inquisitive people in general. Whenever it comes to a news regarding Mars, all of us are excited to know more about the same. So we call Mars as the red planet, but do you know from where the red color comes from? Well, the answer lies in the mineral called jarosite. Good afternoon, everyone. I'm here in methodology. Then I will discuss my results and discussions in a case-wise manner. Then summarize the things and tell some future plan of work. Then I will highlight some prospect of the work and finally cover the references and acknowledgement. So let me start with the introduction. Launched in the year 2003, Opportunity rover identified the presence of jarosite on the surface of Mars in the Meridiani Planum. This mineral was found as a part of finely layered sedimentary rock sequence in the planet. But the history of this mineral dates back to 1987 when Dr. Roger Burns predicted the stability of the mineral under surface conditions prevailing in Mars. Now, let me introduce you all to this mineral called jarosite. Well, jarosite is a part of the alunite supergroup and bears the general formula AB as we see here, AB3TO4 whole twice, OH whole 6, where in the A site we can have either sodium, potassium, or hydronium, rubidium, tantalum, ammonium, calcium, or lead. In the B site, we can either have iron or aluminium, and TO4 stands for SO4 2 minus, PO4 3 minus, and ASO4 3 minus. This group of mineral finds application in acid mine drainage in the mobility of toxic elements and metallurgical processing. It is of great interest to physicists because it has a Kagome lattice and shows frustrated magnetism. Jarosite has been recently found in the deep Antarctic ice as reported in the Nature's Communication Journal recently in 2021. Although the most common N-membered jarosite is potassium N-membered jarosite, Mosby spectroscopic studies indicate the presence of quite significant amount of sodium cation in the site where potassium sits. Even minor element substitution is observed on the other side, such as aluminium sitting in the site where iron is supposed to sit. Previous studies have reported the equilibrium decomposition of jarosite to yavapite, another mineral, hematite, that is iron oxide, and water vapor taking place at around 18 degrees Celsius. Here, in the light of thermodynamics, we have observed the effect of substitution of sodium in the site where potassium sits, that is basically the A site of jarosite, and Al3 plus in the Fe3 plus sites, or basically the B site. we should keep one thing in mind. The stability of jarosite is important because it carries information regarding the chemical, isotopical, and potential biological activity of the geologic past. We have done our calculations and observations using ab initio quantum chemical density functional theory as implemented in the Vienna ab initio simulation package, commonly known as VASP. Now, moving on to my results and discussions. So, firstly, we take the case of pure jarosite and natrojarosite, where pure jarosite basically means the potassium N-membered jarosite, as we see here. And the second is for natrojarosite, that is the sodium N-membered. Now, with the help of thermodynamical calculations, we take a note of the change in Helmholtz free energy. And what we see is that throughout the temperature range considered, delta F, which is F1 minus F2, is positive. What does it imply? We can see from here that F1 is greater than F2, meaning that it requires lesser amount of energy to break down natrojarosite. Moving on to the second case. Before we look at the second case, let me show you once the formula of jarosite, the general formula. Over here, as we see at the top, here in the previous study, A side contained in one case sodium and potassium. Now in the A side, we do both sodium and potassium. This is basically called the jarosite natrojarosite solid solution. So here, the solid solution to decompose, there can be two possible decomposition mechanisms. It might happen so that in the first process, either it decomposes to yavapite, this mineral, like here instead of the pure sodium, we get sodium and pure potassium, we get sodium and potassium solid solution, then hematite and water vapor. Another possible decomposition mechanism is that it breaks down to pure yavapite, and this is the corresponding sodium N-membered component known as elphelite, and hematite and water vapor. Proceeding in a similar manner by checking the change in Helmholtz free energy, here we can see that F3 is less than F4. Please keep in mind that the suffix correspond to the reactions shown here. So F3 less than F4 implies that the more preferential way of decomposition is reaction 3. Moving on to a third case. So we have got the possible energetically or thermodynamically preferable mechanism of jarosite, natrojarosite solid solution. And now we have the pure jarosite, and we do a relative thermodynamical stability analysis. And we can see from the change in Helmholtz free energy that over here, the change in Helmholtz free energy is less than 0 throughout the temperature range considered, which implies that it is easier to break down jarosite, this reaction, compared to that of jarosite, natrojarosite solid solution. So till now, whatever we have done was the relative thermodynamic stability calculations. Now, the two major reactions shown here, that is the pure N-membered forms, these are the reactions actually taking place like in pure N-membered forms. So now what we do is we thermodynamically replicate these two in the vacuum conditions. So on replicating them thermodynamically, we observe the equilibrium temperature of both the cases. That is where the change in Helmholtz free energy will be 0. So what we see is that for the case of pure natrojarosite, that is equation 2, over here, it is about 25.84 degrees Celsius greater than that for the pure jarosite case. Now, I have mentioned earlier that the Mosbel spectroscopic study done at the Meridiani Planum indicated the presence of aluminium in the iron sitting site. So, now we take the jarosite, potassium N-membered jarosite structure and dope aluminium in it as well in the site where iron sits, that is basically the B side. Again, there can be two possible mechanisms of decomposition as shown here, reaction 7 and 8. So thermodynamically, we could see that since the change in Helmholtz free energy is greater than 0, the more preferential way of decomposition is reaction 8. So this decomposition implies that it will break down to yavapite, which will have some amount of aluminium doped in it, pure hematite, and water vapor. Now, finally, we go for a relative thermodynamic analysis of the aluminium doped jarosite and that of without doping aluminium. And we go for a relative analysis and we find that at temperature corresponding to about 778 Kelvin, roughly, the delta F is equal to 0. That is, it is equilibrium. And above this temperature, pure potassium jarosite will decompose. So what we can interpret from here is that above this temperature, aluminium basically stabilizes the structure. So finally, we can summarize as follows that jarosite requires lesser amount of energy to break down as compared to the jarosite, natrojarosite solid solution. So from here we can understand that the natrojarosite solid solution is more stable. And also aluminium stabilizes the jarosite structure above an observed temperature. So as a plan of a future plan of work, we would like to understand the temperature difference with the solid solution of jarosite, natrojarosite. And I would like to highlight some prospects of this work. The presence of jarosite is indicative of the fact that once there was a free flowing water on the Martian surface on the geologic past, as we know. And since jarosite is quite abundant in the planet, its mineralogical signature is important for us so that we can understand the chemical and thermodynamic history of the planet. And as a result, it's desirable for us that the jarosite mineral remains stable under Martian conditions. Now, covering the references, these are the references that I have used for my work. And finally, I would like to acknowledge my debt to my supervisor, Dr. Shostika Chatterjee, for her immense guide and support. And I would like to acknowledge my Computational Mineral Physics Lab of IISER Kolkata and IISER Kolkata Department of Earth Sciences. And finally, Presidency University for this opportunity. And last but not the least, thanks to everyone who has helped me either directly or indirectly for the completion or for this work. Thank you.
Thank you, Ms. Banerjee. Now, if anyone have any questions.
Just a one question.
Yes.
So you said you have used like the here the ab initio to do a density functional. Density functional what we do is like in the Boyle-Mark or a function formula, we assume a set of basis function method. So what kind of basis functions did you use?
Plane wave basis set.
Okay.
Here it is implemented that way.
Okay.
Yeah. Any more questions? Thank you.
কি ডাউনলোড কর বাস ওটা কাট কেটে দে এখানে কেটে দে এখানে দেখ ওইটাকে না অ্যাকচুয়ালি এটা
Now, the next talk would be given by Samit Datta of College of Science, Technology and Agriculture, University of Kolkata. You have 12 minutes.
So which is the pointer? The pointer?
হ্যাঁ আমরা যেটা বলবো
আর পয়েন্টারটা কোনটা? না এটা যেটা কিছু eight last. Oh. पूरा only 8 and point. Only a
এটাতে হলো
Hi, it's a pleasure to be here. So I'm Shomik and this is Parthiv. And we have basically worked on the Fokker-Planck equation. We are basically going to try to solve it analytically in the context of laser cooling of atoms. So at first, let us speak about the Fokker-Planck equation. So I think most of you have taken a graduate course in statistical mechanics, and that is where you come across the Fokker-Planck equation when you're studying systems like the Brownian motion. So it is basically a partial derivative equation of a deterministic equation, because this is basically telling you about the evolution of the velocity distribution. And to simulate a semi-classical description of laser cooling, this is the force term that you take. This is from a laser cooling perspective. And now Parthiv will give a brief overview of what laser cooling is actually.
Okay, so laser cooling is basically a technique to slow down the neutral atoms and thus cooling them. For this, we need 3 pairs of laser beam as shown in the picture. So for this, let us first consider only one laser beam is approaching the atom. So when the atom absorbs a photon, it goes into the excited state, and after a while, it drops back into the ground state and emits a photon in a random direction. So if this process continues repeatedly, the atom will emit photon in random direction, and thus it will lose its energy and cool down. But here's a catch. In a gas, the atoms are moving in random direction. So the atoms which are moving away from the laser will speed up. So to avoid this concept, we introduce the concept of Doppler shift and choose the frequency very low for the stopped atom to absorb. As you can see, the atom which is moving towards the laser sees it blue shifted. I mean, the atom will see the frequency greater and it will absorb a photon. And the atom which is moving away from the laser will see it red shifted, means the frequency it will see is lower and will not absorb the photon. And the stationary atom will not see it greater or lesser. So in this way, we can laser cool an atom using 3 pairs of orthogonal laser beams. That's it. Now Shumik will continue.
Okay, so now that we've got a basic overview of what laser cooling is, we can get on with solving this equation. So at first, as I've told that we are going to solve this deterministic equation, and this is very simple once you take this substitution of v square is equal to z, and you see that this is the integration that follows, and you basically get this condition that z must satisfy this, and incidentally this is the condition with which the Lambert W function is defined, and therefore the solution which you obtain zt is the Lambert W function at this point. And we call the solution of the deterministic equation as V bar, which we have taken without any noise, and this is we call V bar, which is the square root of z. And now this is like a plot of the Lambert W function. Here, this blue line shows the Lambert W function, and this is if you expand the Lambert W function for long times, you can see an exponential decay in V bar. So the next step which we do is, so now we have to include noise in the system. So what we do is we expand the random trajectory V around the deterministic trajectory V bar, which we have calculated from the deterministic equation, and we include a noise factor, which is the square root of D, which is the noise. This is how we are expanding it. And then we obtain, and this was our previous Fokker-Planck equation, but this is not solvable. So that's why what we do is we transform this equation into this in terms of Y, and we define another probability density function Q. We transform it in this form, but in this case, the catch is that Kv, which we had taken to be minus V by 1 plus V square, which was a non-linear term, but we get K prime V, which is a linear term, but this is time dependent. And this is how we are defining K prime V. This becomes non-linear, becomes linear. So it's much more easier to solve. And you can get solutions of closed form solutions of these. And therefore, this is what is written here, that in the limit of small fluctuations, the Fokker-Planck equation with non-linear drift is transformed into another Fokker-Planck equation, but this time with a linear time dependent. And you can obtain solutions of this. And now we are calculating basically the mean and the variance of the velocity distribution. So at first, these are very elementary to calculate through these relations that we see. You can calculate the first few moments, which is basically, we are basically calculating two, which is the mean and the variance. And this is how they are related with the variable y. And now if you evolve these, if you look for the evolution of these variables, which you can do from this equation, because this is time dependent, you have to basically substitute that into, and these, use these and you obtain these equations. And these are easy to solve, these different, because these are first order differential equations, simple to solve. You get forms like this. And now if you plug in these values of K prime into these equations, then you get forms, and this is what you obtain. This is basically the result, where V0 is basically the initial velocity, which is related to the C, which you saw in the deterministic equation. Now, this is the interesting part where we are seeing the plot of this average contribution of the noise. So over here, we can see that for C equal to, so this is basically plotted for two C values. So this blue line is for the C equal to 0.8. Basically, the V0 is less than 1. And over here, for C equal to 8, the V0 is greater than 1. So for V0 less than 1, we can see that the mean noise is basically decaying exponentially with time. So this is not affecting basically the average contribution of the noise is decreasing exponentially with time. So this mostly the system stays near to its deterministic equilibrium, which is the V bar. But when V0 is greater than 1, then for short times, you can see that there is an amplification in the noise. So basically, at this point, the fluctuations are pushing the system away from the deterministic trajectory. And now if you plot the variance, then the variance is basically not initial condition dependent. So the variance you can see is increasing linearly with time. And then as the time is increasing, the variance is decaying exponentially. And this is another process called the Ornstein-Uhlenbeck process, which is basically a linear process where the KV term is linear. And in that we can see that it never increases beyond 1. And and if you do the similar calculation, if you define an autocorrelation function, you define this and you use the same Fokker-Planck transformed equations to obtain this expression for the autocorrelation function. And for this, you can see that there are two plots again. This is also initial condition dependent. So for V0 greater than 1, you can see that there is a transient increase in the temporal correlations, whereas for V0 less than 1, the temporal correlations decrease exponentially. So what is the conclusion and how does it apply to a system of laser cooling? So we can see that all these transient amplifications at shorter times which we are seeing, they're the result of the nonlinear form of the drift coefficient, which is Kv. And this gives us two results in the small noise limit. That is transient noise amplification, where basically we have seen that the noise is amplified for V0 greater than 1. And that shows us that the fluctuations at that point are increasing in the system. So as the fluctuations are increasing, there is a temporary increase in the temperature of the atomic cloud we are trying to cool down. And then we are seeing a transient rise in temporal correlation, and that gives us a larger spatial diffusion coefficient. And like these are some applications of laser cooling where you're seeing you need to construct Bose-Einstein condensates. You need laser cooling to bunch the atoms together. They're used in quantum computing, and they're used in atomic clocks to make precision instruments. And these are the references. Basically, we have reviewed this paper where we have gone through the calculations. This is a paper by Eric Lux, where he solves this Fokker-Planck equation in the small noise limit, and you can go through these references to find out how the kV equal to minus V by 1 plus V, so the nonlinear diffusion coefficient is arising out of. And that is it. Thank you.
So any questions?
Fluctuations in basically fluctuations in the velocity distribution, because we have expanded the velocity. Yes, it is happening because of the noise. The velocity distribution of the atoms, because over here in this context we're using it in the context of laser cooling of atoms. So this is the velocity distribution of the atom. So basically, due to the noise, for a short amount of time, there is a increase in fluctuations in the velocity.
Assume a small fluctuations approximation.
Yes.
So, like experimentally, how can one attain this small fluctuation, like just reduce the temperature of the system or something like that?
Yes,
the
actually.
velocity fluctuations at a minimum.
Okay. The experimental, you want to know how it can be done experimentally?
Like for example, laser cooling is like a very experimental thing, and it is done by experimentalists
Yes,
all over
yes.
the world. So, like, how do they do this thing in real life to keep the fluctuations small?
Okay, for this, so basically what I have said earlier about laser cooling. So when the temperature is high, you know that the fluctuations will be greater. If the temperature is low, fluctuations will be low. So then we can approximate it to d tends to 0. And
yeah,
yeah, right.
Okay, thank
Any more questions? So thank you. So next speaker we have Akash Sharma from Charachandra College.
And close our view.
Just right.
Good afternoon, everyone. My name is Akash Sharma. I'm from Charachandra College, UG, third year. So here today I am presenting a brief description about the muon G-2 experiment. We all know that some years previously there are a thing that physicists have found a new physics and they breached the standard model concept very much, and by the experiment they claim that they do that. It is the muon G-2 experiment. So here the experiment. So it's a experiment that muon G-2, where G stands for the gyromagnetic ratio of muon. Gyromagnetic ratio of muons lies much deeper than it seems. So what they do that they take a muon, create a muon, and they want to note the gyromagnetic ratio of the muon. So they do that the gyromagnetic ratio, and they found a discrepancy of the theoretical value that standard model predicts, and what they found by the experiment. So here are some questions that we may ask: that why we need this experiment? So we all know the vacuum, but vacuum is not truly empty space. There are virtual particles pop in and out with existence for a very short amount of time. So we don't know about them, and we don't know the characteristics about the virtual particles. So we want to find the virtual particle and their characteristics. So this experiment is needed to do. So there are so many particles, and why we choose muons to do the experiment. So muons are like electrons, point particles. It has no other constituent particle like proton that they have quarks and other things. So it's the energy of muons is totally its fundamental energy, not the other fundamental particles or the elementary particles contributed the energy in the muons. So another reason is in 207 times heavier than the electrons, which makes it more sensitive towards the new particle. And the lifetime of muons is 64 microseconds, which is much longer to help the scientists to gather the information that they need. And what is G-2? Inefficiency of the experimental setup or the human errors, and what we can say. So this is now 4.2 sigma, and further experimentals say that it can go higher and eventually further discussion. If we see that it's not much that all I that say that written in here. So I have gotten help from the Wikipedia, the Fermilab official website, and a book to study muons. We all know the Griffith's particle physics book. And finally, I will end up. This is the magnetic ring that placed in the Fermilab. This is the This is the way the muons came to the magnetic ring, and in here they calculate the gyromagnetic ratio of muons. So it is the whole total lab where the thing is happening. So thank you very much. I would like to thank the Precision Committee and the Presision University for giving me this opportunity. Thank you.
Thank you, Akash Sharma. If anyone has any questions.
So you said you showed the largest for the last. Sir, this one, yes. So this one, if I remember correctly, this was the 4.2 sigma is around the value of G, the ratio. So how do you say that from that one can the virtual particle production, particle existence? How we infer from that? If G is is the anomaly, there is a value anomaly in G. So how do we incorporate or get idea that there is a virtual particle other than this? Because if G has an anomaly, and then there is something wrong in the S value. So the S value has to be commute with my what Dirac has said with the Hamiltonian. So that's G value will change with that. So my question is that is it? I don't think is it really 10 hours virtual particle? I may not know. So that's my question.
Actually, what I have read to the articles that they said that the empty space is not really much empty, and there are more virtual particles which comes into existence for very short amount of time. And the gyromagnetic ratio of the muons, when we rotate the muons, then there are some of the particles are pops in and out, then affect the ratio, the fundamental, the experimental value. And they call that there are new kind of particles that we don't know that contributed in the gyromagnetic ratio. So that's all I know. It's
Okay, thank you.
এই তো সবুজ মন্ডল। Present হবে। দেখছি। তো একটা
So next talk will be given by Shantanu Vishwas and Shobik Mulder of Rajabala Science College. You may come.
জুম করতে হবে, জুম করতে একটু জাস্ট একটা এটা দিয়ে জুম করতে, এইটা দিয়ে ল্যাপটপেই করতে হবে, ল্যাপটপে যেটা আমার স্লাইডটা বানানো না, এটা কি দেখা যাচ্ছে?
হ্যাঁ, এটা দেখা যাচ্ছে, এটা দেখতে অসুবিধা হচ্ছে। সরি,
থেকে বেশি জুম করলে কিন্তু এগুলো কেটে যাবে। এখান থেকে আয়, তাহলে একটু ইয়ে করতে পারবে, এটা করবে এইটা এইটা কন্ট্রোল করতে পারবে, কোনটা এইটা ঠিক আছে, এটা দাও, এটা বলবো মানে 3 মিনিট এ বলবো, 2 মিনিট মানে কোয়েশ্চেন আনসার, নাকি পুরো 5 মিনিটের
পুরো 5 মিনিটের টক, তারপরে বাকিটা কোয়েশ্চেন আনসার।
না অ্যাকচুয়ালি আমাদের তো 3 মিনিট বলা হয়েছে, আমরা 3 মিনিট হিসেবে প্রিপেয়ার করি। আচ্ছা ঠিক আছে, ফাইন, 3 মিনিট মানে করতেই চলে যাবে।
Hello everyone, I am Shantanu and this is my friend Shobik. First of all, we would like to thank the organizers of Presision for giving us this opportunity to present our poster in front of this audience. Now, as you can all see that yes. As you can all see, the topic of our poster presentation is entropy and enigma of physics. Now, what do we actually mean by this entropy? The entropy is nothing. The entropy of a system is the degree of disorderness of that system. From the second law of thermodynamics, we all know that the entropy of the universe is always on the increase. That means the entropy of the universe never decreases. Now we have this Clausius theorem which tells us that the closed integral of dq by t is always less than or equals to 0 for any reversible process. Now next, if we want to look at entropy from a statistical point of view, then we are given with this Boltzmann relation which connects the entropy of the system to the number of accessible microstates, which is denoted by omega in this slide. It is given by S equals to kb ln omega. And as you can all see that the number of microstates is clearly directly proportional to the the entropy of the system is directly proportional to the number of microstates available to that system. Now, if you look at an ordered system, the number of microstates is always less than the number of microstates of an ordered system is always less than the number of microstates of a disordered system. So the entropy of an ordered system is always less than the entropy of a disordered system. As you can all have seen from that equation, it also proved that S equals to kb ln omega because the entropy is directly proportional to the number of microstates of the system. Now the rest of the poster presentation will be carried forward by my friend Shobi.
Thank you, Shantanu. Now our next topic is the information and entropy. Now you may wonder that what bits and bytes have to do with heat engines and the refrigerator, but there exists a deep connection between them. Now as the information increases with time, that means the number of microstate increases with time, the entropy increases and the vice versa happens. Now, for example, an organized bookshelf always tend to mess up, or an iron clothes always got wrinkled. Now comes the Maxwell's demon. Now it is a hypothetical intelligent being capable of detecting and reacting to the motions of individual molecules, like as you can see in this picture. I suppose this is the demo. And this was introduced by the James Clerk Maxwell in 1871 to illustrate the possibility of violating the second law of thermodynamics, which will actually indicate the perpetual motion machine. Now the next topic is the entropy and the arrow of time. Now any natural process always occurs in such a direction that it causes an increase in the entropy of the universe. Now comes to the entropy of the black holes. Now, as you all know, that black hole is an object in space from which nothing, not even light, cannot escape, and it is surrounded by a mathematical surface called the event horizon. And Hawking and Bekenstein gave us a formula relating to the entropy of the black hole and the surface area of the event horizon, and which is related to this equation, where A is the area